Okay, so our next speaker is Daniel Holmes from Vienna, is the Institute of Science and Technology in Austria. He's going to tell us about Schubert varieties with infinite quantum products. So please take it away, Daniel.
Thank you very much for the invitation. It's very nice to give this talk here today. And yeah, so the topic of my talk today is part of a bigger project at the intersection of Gromov-Witten theory on the one hand and GKM theory on the other side. But I thought that for a short talk like this, a nice little application is maybe best suited. Um, and at the same time, I will advertise a little our new tool, software package that deals with GKM spaces and we hope might be useful for some of you. So, oops, yes. So the question, the story begins in June earlier this year, where Professor Mihalcha asked me the question whether there exists a smooth Schubert variety with an infinite quantum product. And the motivation for this is, of course, in quantum Schubert calculus, which traditionally studies quantum cohomology or equivariant quantum cohomology of homogeneous spaces, and relatively more recently also looked at that of Schubert varieties. So to start the setup for the talk, we'll take a complex Lie group G, simple and simply connected. We'll take some parabolic. We'll take a maximal torus in there. W for us will be a coset in this quotient of Weil groups. And XW will be the Schubert variety associated to that. And so the picture you see here is a forecast of the GKM graphs we'll see later that bring this whole story into combinatorics in a nice way. So I'll quickly say what quantum cohomology is, just in case. So for a smooth projective variety X, let lambda be the so-called quantum coefficient ring. So for us, this will just be the semi-group completion of the effective curve classes, including zero. And that's just to say that a typical element in this lambda is a possibly infinite sum of elements of the form q to the beta, where q is just some formal variable, and beta is a curve class in second homology. And then the quantum cohomology as a module is just the ordinary cohomology ring. We'll take rational coefficients and tensor with the quantum coefficient ring. Things get interesting when we add the quantum product, or correctly, the small quantum product on this module. And we define it here using Poincare duality. So for A and B cohomology classes, we just say what its pairing against any other C is. And in the sum on the right, you see q to the beta from the quantum coefficient ring to keep track of the curve class. And the coefficient is just a Gromov-Witten invariant in genus 0 with 3 marked points and in class beta. And naively speaking, what this Gromov-Witten invariant should be, it should be a count of rational curves in class beta passing through cycles Poincare dual to A, B, and C at the respective marked points. Of course, this isn't always true. This is not necessarily enumerative, but that's not the topic of today's talk, so we're not going to that. The important thing about this ring for now is that it is, in some sense, a deformation of the ordinary cup product on cohomology, in the sense that when you look at the q to the 0 term, that's precisely the ordinary cup product. And also, oops, sorry, now I need to move the zoom. Yes, it's commutative, associative, and unithal, where the star next to commutative is just for graded commutative, but in our case, everything cohomology is concentrated in even degrees, so we don't need to worry about that. And importantly for later, you can make this product behave well with respect to the cohomological grading. And to achieve that, you need to give q to the beta the grading 2 times the Chern number of beta of the curve class. And here's a typical example that is probably well known for Pn. And you see how you recover the ordinary cohomology when you set q to 0. So this finiteness question, so the finiteness question really means is it possible that in some quantum product we have infinitely many terms, infinitely many q to the beta terms? And this wouldn't be an interesting question for homogeneous spaces because of this well-known lemma, which just says that if every curve class, apart from zero, of course, has a strictly positive Chern number, then these quantum products are finite. And the reason is just by the grading. You just look at all the possible curve classes that could contribute. You see that by the grading, the Chern number is bounded. But also if every possible constituent of a curve class has a strictly positive Chern number, then there are just finitely many ways how you can contribute to this product. And in particular, this applies to homogeneous spaces. So the question is not that interesting there, but it is interesting for Schubert varieties. So to tackle this, we'll use the GKM nature of Schubert varieties. So here's a quick recap of what a GKM space is. For us today, it's a smooth projective variety with a complex torus action that should have only finitely many fixed points, also known as zero-dimensional orbits, and finitely many one-dimensional orbits. And to this, we associate a combinatorial gadget, the GKM graph, whose vertices are the fixed points, and whose edges are the torus stable P1s. And in addition to that, the GKM graph has the datum of an axial function, which assigns to each edge plus a choice of orientation a weight in the following way. So an oriented edge is just a t-stable P1 plus a choice of one of its two fixed points. So we just take the tangent space of that P1 at this fixed point and assign to it its torus weight. And here's an example of such a resulting GKM graph. It's a full flag variety for C3. The weights are marked for some of the oriented edges. And the vertices are given by elements of the Weil group, which is the symmetric group on three elements in this case. So to apply this in the Schubert setting, to solve the question that we saw in the beginning, let's see what the GKM graph is here. So Gilliman, Holm, and Zara in the paper wrote down the GKM graph for the homogeneous space in this case. The vertices are just the cosets as we saw before, and the edges and the axial function takes a very nice shape as well. And here's the same example as before, the same full flag variety for C3. And what you see in red here, so everything from 312 downwards, is the GKM subgraph, that is the GKM graph of the Schubert variety given by this Weil group element 312. And you see nicely here how you just pick your W or your coset more generally, and you close down to get the, you take the downward closure in the Brucher order to get this graph. Okay, so what does this GKM business buy us? Very briefly, of course, equivariant cohomology, according to the GKM theorem, or to this whole toolkit. An element of equivariant cohomology is just a polynomial in the equivariant parameters at each fixed point, subject to certain compatibility conditions given by each edge of the GKM graph. Also, you can integrate, of course. So a Tier-Bot is well known. You just reduce an equivariant integral to the fixed points and knowing the normal bundles at those fixed points. And in particular, important for this story, equivariant Gromov-Witten invariants, which are defined formally as an integral over this fancy M here, which is the moduli space of stable maps to X in class beta with genus G and n marked points. For us, we'll always have genus 0 and 3 marked points for the small quantum product. So to actually calculate such an integral, one typically uses that the torus action carries over to the moduli space just by post-composing a stable map with the torus action on the target. And the amazing fact in the theory is that a Tier-Bot style equivariant integration still works with respect to this torus action. So to do that, of course, as before, we need to know the connected components of the fixed locus, and we need to know the normal bundle and its weights. And this was worked out in detail by Leo and Sheshmani not too long ago. So they wrote down a very explicit description of the term in the localization formula for each component of the moduli space. But there was some small gap to be filled in how to actually compute all of these components, which I will get to in a second. And also the formula explicitly requires for each torus stable P1 in X, knowledge of the splitting of the normal bundle into linear sums. And in general, the tricky bit is that I'm not sure that we can determine these from the GKM graph itself, and especially for an abstract GKM graph and any compatible connection, that's not necessarily the case. But we'll see a workaround in a second. Okay, this slide here, don't worry, there is no time for me to really explain this anyway. It's just an illustration of the combinatorial structure that indexes the fixed components of the moduli space. In this case, genus 0, and the target is CP2, which is P2. The important thing to take away from this slide is just that the fixed components on the moduli space that we need to integrate over are given by certain decorated trees, or in positive genus decorated graphs, where they're called gamma with a decoration here, where the decoration consists of a map of graphs to the GKM graph, edge multiplicities for each edge, so that D1 plus D2 plus D3 plus D4 is beta. So these will determine the curve class. In this case, it's easy because curve classes on projective space are simple. In general, there was something to be done, and we keep track of where the marked points are, of course. Okay, so that's the combinatorial structure. Once we know all of those decorated trees, we know all the components that we need to consider, and we can apply the Liu-Shishmani localization formula. So here's a little result that allowed us to actually take the formula. I should have said at the beginning, sorry, this is joint work with Giosuè Muratore in Lisbon. This small result allows us to take the localization formula and really implement it in a computer effectively for any GKM graph. So the first result is that we can actually compute and iterate through this set of fixed components. And mathematically, what's behind this is just an understanding of the relations of the curve classes. So in what was easy in projective space, in general, there is, of course, some other recipe how you can determine all the relations of those curve classes. And much more importantly, even is that this splitting business of the normal bundles actually turns out we don't need it. So even though we don't know, or I don't know at least, how to determine this splitting, basically after staring at the localization formula for long enough, we realized, okay, we don't need to know it precisely. There are some constraints that we know, and this is enough to compute the term for each connected component of the fixed locus. Okay, and with this, we implemented this in a software package. We called it GKMtools. And apart from implementing the most important examples of GKM spaces, including, of course, Schubert varieties, it supports cohomology, integration, curve classes, but of course, importantly, Gromov-Witten invariants and quantum cohomology. Recently, we also added positive genus and more features to follow. So, and in particular, we are happy for any feedback on this software package or any comments how to improve it, and also happy to help if you have a specific application in mind that you would like some help with. Anyway, how do we actually use this to solve the initial question? So from the lemma that we saw in the very beginning, this finiteness criterion, we should better look for some Schubert varieties where some Chern number is 0 or possibly even negative. So to do this as an algorithm, that's actually how we found these examples that we'll see in a few slides. First, we fix some root system, so that gives us some group G. Then we iterate through the possible parabolics, the possible homogeneous spaces for this. Then we iterate through the possible Schubert varieties. Okay, we throw away those that are not smooth, because we are in the smooth business here. And then we check if any of the curve classes here has non-strictly positive Chern number. And this would be a lot of work by hand, but with our tool, it's straightforward and a matter of a few seconds. I mean, the whole loop, actually, for small enough types. Okay, and so here's the result of what we found, basically some examples that we found. What you see here are the GKM graphs of two smooth Schubert varieties in type A3 that have infinite quantum products. And I'm going to say how we know that they have infinite quantum products. Because, of course, having a software tool is nice, but we cannot perform infinitely many calculations, obviously. So the theoretical result that allows us to draw this conclusion is from our recent paper, which is also on the archive, of course, that applies in the particularly nice situation here. The nice situation is when we have a GKM graph in complex dimension 3, where all the Chern numbers of edges are positive, except a single one which has Chern number 0. In this case, the nice thing is that in this big localization formula, we get control over the graphs that usually we don't have. So in particular, all those decorated graphs, all the edges, will have to lie on the Chern number 0 edge if we want to produce a Chern number 0 curve class. So for those curve classes, we really we have a chance of understanding what goes on in terms of localization. So what we did is we looked at this situation also before the Schubert application. That's the topic of this talk. And looked at what the possible GKM local models for this situation are at the Chern number 0 edge. And it turns out there are not that many. We analyzed them. And in each of those cases, you get infinitely many non-zero terms, at least for the Q beta, where beta has Chern number 0. So effectively, this means the non-zero stuff, the infinite non-zero summons occur in those curve classes that are just multiples of the class determined by the Chern number 0 edge. Okay, so that's that. Yeah, so that's the answer to the initial question. And I would like to close this talk by briefly mentioning a fun example in type G2, because of course, why stop in type A? So this is the GKM graph of a smooth Schubert variety in type G2. And here the reasoning from before does not apply immediately, because we have not one but two Chern number 0 edges, and all the others are positive. But we can still draw a conclusion which is slightly weaker. Instead of a quantum product with infinitely many terms, we get an equivariant quantum product with infinitely many terms. So, and the example in this case would be, I think you have to choose the right point, probably S1 or the identity would both work. You take the quantum product with itself. But the problem or interesting thing in that example is that when you set the equivariant parameters to 0, you recover 0. And we played around a bit, not excessively long, but we did try to find some non-equivariant quantum product that doesn't vanish, or that doesn't have infinitely many terms, sorry. And we couldn't find one. So here's maybe a fun little question for further playing around with our tool or theoretical investigation. Is there actually some quantum product on this space that has infinitely many terms, and that is non-equivariantly and not only equivariantly? And with that, I thank you for listening. Thank you again for the invitation. And yeah, looking forward to any questions you may have.
Thank you very much. A beautiful talk. Thank you.